Hi, good morning, everyone. So welcome to today's webinar. Today is Saturday, 8th March 2025. This is our fifth webinar of the year. Since January, we have completed four, and this is the fifth webinar of the year. Overall, probably we would have done 135 plus webinar since last one year, or I would say 180 since last 2 years. Earthing of HV lines and transformers 11 kVA to 33 kV at industrial and commercial premises. Safety and reliability requirement, that is the theme of the webinar today. And this webinar is organized by NFE, National Federation of Engineers for Electrical Safety. My name is Dominic, founding member and event chairman, and I'm honored to be your host for the day. So as we celebrate our second year, today, 6th of March, we completed our 2 years, just 2 days back. So we had a grand celebration in Ahmedabad, supported by Gujarat government. And we are one of the fastest growing society in India. In less than 2 years, we have over 2,000 people. We have done 39 seminars across the country. And as I said, almost 190 webinars. Overall, we put together, I connect over 78,000 people in last 2 years. This is not only in India, we have also covered globally. And also today's webinar is a record registered. We have over 1,350 registered for today's webinar. That shows the popularity of NFE and also the speakers. Well-respected personality in the electrical industry and is in the most demanding and most sought after speaker, not only in India, globally. So today's attendees are included, we have electrical engineers, safety professional, consultant, industry leaders who are committed in enhancing electrical safety in industrial and commercial segment. So we are privileged to have our president of NFE, S. Gopakumar, a distinguished expert in the field who will share his deep insight and practical knowledge on the vital topic. So before we introduce the speaker, I would like to talk about a few seconds of about NFE, who we are and what we are. And average, we get 25 to 30 members every day. So it's a great opportunity for those who are attending today's session but not member of NFE. I would urge you to take this opportunity to become a member. So you go to the website, you will see the screen, creating awareness on electrical safety, become a member. In less than a minute, you can become a member. If you click on that, become a member, you have various choice. What is our vision and mission? To make every electrical installation free of accident, such as electrocution and fire due to short circuit, and increasing the reliability and electrical installation, thus contributing to the saving of lives and property and supporting sustainable development. Our mission, we shall strive to achieve our vision through getting accredited. Our products, personal certification, we shall focus on electrical safety by design, manufacturing, installation, and maintenance of electrical product. As we may be knowing that we already started our certification program. We have already 8 members who've been certified. It's an ongoing process. You go to our website, there is a program, on the menu, we have a program, you click that, and also schemes. You go to click on the scheme, you will get a lot of information about our certification program. If you want to watch our previous webinars or various subjects that we have covered, you have to go to blog, which will take you to various standards and codes and discussions, blogs and all that. But for that, you have to be a member. Only member can access to these information. Hence, I request you to become a member of NFE. So it's very simple. We have individual member, we have corporate member, we have MSc member, and this year we are expanding length and breadth of the country by establishing student chapter. Every engineering college where there's electrical department, we have to have a chapter. So those who are attending here, those who are students or member of certain colleges, we welcome you to interact with us to set up our student chapter in your college. And also, we have started a mass awareness program where we will be training the college faculty and engineering student will reach out to schools. So we have planned to cover 2,500 schools across the country, around 250 student chapter across the country. I also like to inform you, totally we have now 10 chapter across the country. Our management and entire member committed, where there is electricity, we have to have a chapter there. We have to have a member who will educate the rural areas, educate the people who are in the field, who are playing with electrical equipment. That's the mission of NFE. Our speaker is a well-known figure, most of you know. He's an electrical engineer and the founding and promoter of Cape Electric Private Limited, Cape Electric Power Production Private Limited, LP Consultants International Private Limited. And BAS is very closely associated with them and is a member of ETD 20, ETD 30, ETD 50, and also taking an active role in National Building Code 2016. Now under revision, which is expected to release by end of this year. It will be called National Building Code 2025. He is also a very active member on IEC TC64, TC81, AC37A. So we just finished Ahmedabad workshop 2 days back. Attended over 550 people in the Ahmedabad Management Association. And immediately after 2 days, we are here. If you see our track record, every month we have 2 to 3 webinars on various subjects. We need your support, continuous support, not just by registering. We would like you to become a member of NOP because to cover the entire nation, preaching on electrical safety, we need more than 10 to 25,000 members. I urge you to become a member and look forward to see you soon. I give the stage to our speaker, Mr. Gopal Kumar. Sir, over to you, sir.
So I hope my voice is clear as usual.
Clear, sir. Yes.
Yeah. Thank you very much, Mr. Dominic. Now, 2 days back, we had one of the biggest show of NFE, which was in Ahmedabad. And today we are going to have another big show. I'm surprised to see that. I think already about 450 people are there. Seeing through I think today we will cross our records, probably. Let me share the screen. I think my screen is clear.
Yeah,
and
clear.
It is in full screen.
Yes, sir.
Yes. So let me switch off my video so that to make it more effective. Good morning, all participants. Today we are going to discuss a confusing subject, let me say, or sometime a subject which is of a lot of interest, but sometimes it creates a lot of confusion within the electrical engineers. So we are going to talk about the earthing of high voltage lines and transformers, especially between 11 kV to 33 kV. That means you have a distribution transformer. The primary side is 11 or 33 kV, and the secondary side is a low voltage installation. Maybe a distribution transformer or maybe a transformer in an industrial or commercial premise. Today we are going to discuss about the touch potential and step potential during fault in the high voltage system and their limits. Means what are the limits of touch and step voltage which has to be below the tolerable limit in order to avoid shock to human beings. Also the stress potential of low voltage during a fault in high voltage and their limits. So probably I will also try to explain a little bit on what kind of measures we can do to get safety from these or to keep the potentials within the limit. So now first is to talk about the threshold limits of the current through the body. I'm sure all of you are aware, and in all our seminars, Mr. Krish used to explain this particular the current threshold limits, current and time threshold limits in detail to the participants. What is this 30 milliampere? In case of 30 milliampere, what is the duration? 300 milliampere, what is the, or 5 times IN, 150 milliampere, what is the limit? All these are very well discussed. But now please note that this zone, time and current effect of AC current on human body when passing from left hand to feet. This current 30 milliampere, which we conveniently say for an RCD of low voltage, is applicable. This current limit is based on the current which is flowing through the left hand to feet. Now we have to look at an interesting figure, interesting fact or interesting subject, which is called as the current factor. You can find this information in the IEC standard, which I have just shown you in the previous IEC standard, especially 60479. You see here, the current, the heart factor is a factor set by the standard to decide various probably touch voltage and step voltages. Now, for example, left hand to left foot, right foot to both feet, the current factor is 1. So whatever the touch voltages which is there in this particular the graph we are supposed to meet AC1, AC2. Don't go to AC3 and the higher ones. Now, what is interesting to you to look is, you look at the last line, left foot to right foot. That means the step potential, in case of no touch potential, only step potential, means a person who is standing in the vicinity of the substation. The step potential, the heart current factor is 0.04 is the factor. Similarly, you see chest to hand 1.13, 1.3. Chest to left hand, because the heart is on the left side of the human body. That is why left hand to foot, and you see right hand to left foot 0.8, left hand to right hand, hand to hand, the touch voltage, the heart factor is 0.4. That means, in simple, if we evaluate from this particular table, what you will understand is a current of 255 milliampere hand to hand has the same likelihood of producing ventricular fibrillation as a current of 90 milliampere left hand to both feet. So imagine we are talking about 30 milliampere left hand to the feet, and in this particular case, the current through the leg to leg, through the foot, is 0.04. It is multiple times more. Now, from these two tables, the touch voltages are calculated in the standard and the limits are set in the standard. For example, for 1 second disconnection, 115 volt is the leg, hand to leg touch voltage. If we calculate the same potential, step potential, it comes something about 2850. You multiply it by, you have to calculate as 0.04 is the heart factor. So basically, in a typical situation, if we say 115 volt is the touch voltage, the same condition, the step voltage can be 2850. These figures or these parameters can be calculated from the heart factor. Now, please note that in the presentation, I will be using some arbitrary figures. This is just to explain. For accurate figures, you have to look into the standard and read and understand. In order to save time, I am using some arbitrary figures. But now this one is not arbitrary figure. This is from the standard. Permissible touch voltage recommended in IS IC 61936. This is the IC 61936. What does this mean? If you are getting a shock from a touch voltage, either the shock intensity has to be limited to less than this particular graph, or disconnection should happen before the touch voltage crosses the limit, or so on. The permissible touch voltage is based on weighted average taken from 4 different touch voltage configurations. Anyway, this is from the previous standard. I don't explain here. Example, if we are talking about the tripping time of the circuit breaker during a high voltage fault, the touch voltage, maximum allowed touch voltage is 115 volt. If we are talking about the disconnection time as 3 seconds, then the maximum allowed touch voltage is 90 volt from this particular graph. This is the recommended figure which is there in the standard IEC 61936 part 1. Now the standard also explains you how to calculate the touch voltage and prospective touch voltage. If a country or if any installation need a touch voltage other than this particular graph, you can use these calculation and you can arrive a figure which is different. For example, in UK, the BSEN 50522 in the national annex, they use a different touch voltage chart. As you can see here in the IEC chart, the 10 millisecond, the touch voltage is about 800 volt, whereas here they have reduced to something below 500 volt. Example, in 1 second in UK, the touch voltage has to be reduced to less than 80 volt, whereas in the IEC standard, what is recommended is less than 115 volt. Now the standard gives the annexure which can be used to calculate a figure. If you want, you can calculate such figures. But anyhow, the IEC figure stands good for the application like India. On the other side, IEEE 80 gives a different figure. As you can see here, the prospective touch voltage with respect to time. Now there is no upper limit if the disconnection is happening within 100, you see 30, 40, 50 millisecond, then there is no upper limit, whereas the IEC makes certain upper limit. And this curve is also based on a different assumption, or an assumption which is a little bit different from what is explained in the IEC standard. Anyway, let us skip this particular. What exactly we are talking? ZT is the representation of the body. In case of a shock, that means there is a touch voltage. A person is touching somewhere, let's say left hand to feet. He is touching, the current is flowing through the left hand, through the heart, through the feet. So now we have the ZT is the impedance of the representation of the human body. Permissible touch voltage is the limit of touch voltage UT. Permissible touch voltage means what maximum touch voltage, what is the limit of the touch voltage over which a person gets ventricular fibrillation is the question. Now RH and RF represents additional resistance in the body where skilled people are working. For example, you are the technician who is in the substation, he is wearing a gloves. RH is the hand resistance which represents the gloves, and RF is the foot resistance which represents the resistance of a shoes plus maybe the resistance of the gravel. Now, in a typical situation in a large substation, we are the skilled people are supposed to go with the proper PPEs. Under such condition, there is one more parameter which is called as prospective permissible touch voltage. The definition of prospective permissible touch voltage is the limit value of prospective touch voltage UVT. So touch voltage is the effective voltage between conductive parts when touched simultaneously. Permissible touch voltage is the limit value of touch voltage. That means what maximum you can allow. The first one is the actual voltage. The second one is what maximum is allowed. Prospective touch voltage is the voltage between simultaneously accessible conductive parts when those conductive parts are not being touched. Prospective permissible touch voltage is the limit of prospective touch voltage, UVT. I am just explaining you to inform you that during evaluation of a substation, the earth electrode or the touch voltage testing of a substation, All these values are required or to be considered. For example, the glove resistance, the shoes resistance, we can simulate it in a software, or we can even calculate it in a practical condition and do it. For example, this one, what you are seeing, the last one, figure number 1, is the IEC recommended, the 61936 IEC recommended permissible, the tolerable limit of the touch voltage without any additional resistance. Means there is no gloves, no shoes. So you have already seen this particular graph, the figure number 1. Figure number 2 explains RF. RF is the resistance of the footwear. Let's say you have a small footwear, 750 ohm. So in that case, the permissible touch voltage is higher. If your shoes is having a higher resistance, then number 3, the permissible touch voltage is even higher. If you have a very good shoes, very good gloves, then you see that touch voltages are higher. But practically in a substation which we see on the roadside belonging to the distribution company, there is a common man or normal people are going to either touch the extraneous parts or the fence or whatever. And most of the cases, our transformers are also in exposed areas. So there is likely a chance of people without shoes, without protective gears touching and getting electrocuted in the vicinity. So in a typical situation, the graph number 1, where I'm moving the cursor, this is applicable. That means in 1 second, the touch voltage has to be limited to maximum allowed touch voltage is 115 volt. Similarly, step potential. Step potential, I have a better graph. Step potential is totally, as you can see, 115 volt touch potential is equal to 2800 or 2850 volt step potential for creating a similar ventricular fibrillation equal to 115 volt left hand to feet touch voltage. The step voltage here, let's say example 2800 or whatever, but you see 10 to the power of 5, 2 into 10 to the power of 5. Now, by added resistances, for example, footwears and PPEs, the step voltage also, the permissible value of step voltage also goes up. So we have to consider the condition where a person with barefoot, bare hand is operating, or the location is restricted for people with PPEs such as gloves and shoes. So all these subjects are to be considered when we talk this particular subject. I'm showing you this as an example. Coming back, the second subject which also to be considered in case of a fault in 11 kV 33 kV system is failure of electronic equipment in the consumer premise. These two are two news from the newspaper. High voltage damaged electrical appliances. Voltage fluctuation damages appliances worth lakhs. Such news is quite common in our country. Example, a fault on the HV side of a transformer, maybe the surge arrestor failed. At the same time, maybe hundreds of houses, LED TV is gone, or electrical appliances are failing. Refrigerator is burning, inverter is burning. Such failures are due to the transfer of the potential from the high voltage side of the transformer to the low voltage side of the transformer. Now the regulation as well as the standards made limits. For example, the maximum limits in the standard is explained in IS 732 clause 4.5. You can find this kind of a picture. You can find the calculations again in a table. Depending upon the system, for example, you are talking about a TTN system. I have a better picture. I will explain in the next slide. So basically, based on the system earthing, based on the HT and LT side is connected together or separated, there is some calculation we are supposed to do. And the most important is we are supposed to limit the voltages below certain limit. I just put it in an animation. For example, you have a high voltage transformer. The transformer, the brown color line is the transformer HT earthing, let's say high voltage earthing, which is RE. RE is the earth electrode resistance. You have the low voltage winding of the transformer. Imagine the low voltage neutral is also earthed or connected to the reference point. The question which you always be asking whether RE and RB, the ST and LT side, together or separate. Now a fault in the HV side of the transformer can create three problems in your installation. A HT fault is creating a voltage stress on the LT side of the transformer, a voltage stress on the connected equipment. Example, 100 refrigerators in 50 houses burned, LED TV in 25 houses burned. These are due to the transfer potential or stress potential U2. And the third one is a person who is touching any metallic object at the consumer premise. For example, here the person may get a shock during a fault on the high voltage side of the transformer. So basically, a fault on the high voltage side of the transformer is also creating multiple problems on the low voltage side of the transformer. And all these problems, such as U1, which is the stress voltage in the HT side of the transformer, U2, stress voltage at the LV side of the transformer, UF, fault voltage. Please note that U1 and U2 is stress voltage and UF is the touch voltage or fault voltage in a low voltage installation during a high voltage fault. These three problems must be limited. Let us see what exactly is this. For example, there is a fault here. The fault current IE is going to the earth electrode. There is a voltage gradient. Gradient in the sense the potential of RE, where I'm moving the cursor, the potential of that particular point goes to a very high level, which is equal to IE into RE. UE is the GPR or EPR, earth potential rise, or the potential rise is equal to the multiplication of IE is the earth fault current or the current which is flowing to the earth electrode. Please note that all these standards, as well as in my presentation, I will be using 2-3 terms. One is IF. IF is the fault current. IE is the current which is going through the earth electrode. And there is a fault current flowing through the metallic fault return path, such as the earthed conductor in an overhead line or through the shielding in an underground line. So there are different terms used. Basically, the potential gradient or the peak of the EPR is equal to the earth electrode resistance multiplied by the current which is flowing through. Example, imagine the fault current is 5 kiloampere, the current going to the earth electrode. Of course, in no condition a 5 kiloampere current will flow through the earth electrode. This is very, very rare, but just for your information, imagine 5 kiloampere current goes through the earth electrode. Imagine the impedance of the earth electrode is 1 ohm. The UE means the touch voltage or the gradient or the EPR, earth potential rise in that particular point is almost equal to 5 kV, 5000 volt. A person who is touching the metallic object in the high voltage installation, of course, he will get a shock because 5000 volt is much higher than the tolerable limit of touch voltage. The person who is in that touching any metallic objects on the substation, he will get a shock. A person who is touching in the low voltage equipment connected to the same transformer also may get a shock if you don't take care of that particular potential. Connected equipment also will fail if you don't take care. The high voltage side of the transformer also may fail. It all because of this potential gradient, the EPR or the GPR, which is created because of the current flow, the fault current flow to the earth electrode. The limits, the maximum touch voltage in any location, irrespective of high voltage or low voltage, depending upon the disconnection time, is given here. For example, 0.1 second, let's say for example 100 millisecond, then the potential is about 655 volt touch voltage. 0.5 second to 25 volt, 1 second disconnection means the circuit breaker will trip your design is for 1 second, under that condition, the touch voltage is about 115 volt. And if it is 3 seconds, it's approximately 90 volt. This is the maximum allowed touch voltage. That means in the previous slide, if we look, under any condition, a person who is standing in the vicinity or closer to the transformer and touching any metallic parts of the transformer, the touch voltage has to be limited to less than 115 volt if the disconnection time is 1 second, or the touch voltage has to be limited to less than 90 volt or 85 volt if the disconnection time is 3 seconds. That is what we get from this particular chart. This particular table or this particular chart, you will be able to see in IS IEC 61936, IEC 6036444, also the IS 732, the same touch voltage, tolerable limit of touch voltage explained in all the standards. The second one, stress voltage. What exactly is this stress voltage? Stress voltages are, there is a fault on the high voltage side of the transformer. Stress voltage means, here I am moving the cursor, means a voltage between the body of the transformer to the winding, or a voltage between body of the connected equipment to a live conductor is the stress voltage. Now, the tolerable limit of stress voltage. Here, there are two systems considered. Up to 5 seconds, greater than 5 seconds, or you can see less than or equal to 5 seconds, greater than 5 seconds. This means the disconnection time of the high voltage side of the transformer in case of a fault on the high voltage side. There are two times explained here: solidly earthed system, less than or equal to 5 seconds. Impedance earthed system, more than 5 seconds. In a solidly earthed system, 5 seconds means the maximum voltage, the stress voltage has to be limited to less than 1200 volt. You can find it again in the standard 61936, IEC 60364, as well as IS 732. So greater than 5 seconds relate to the high voltage system having long disconnection time, for example, isolated neutral or resonant earthed system. Less than or equal to 5 seconds related to high voltage system having short disconnection time, for example, low impedance earthed system or directly earthed system. Now, the standard IS 732, clause number 4.5.2.3, it explains who is responsible for limiting this voltage. Please note that limiting this voltage lesser than, say, for example, solidly earthed system, less than or equal to 5 seconds, 1200 volt. The consumer cannot do anything. The consumer is helpless in this particular case. It is the owner of the transformer who is supposed to take care of, or who is supposed to limit this voltage. If the transformer belongs to the distribution company, then the distribution company should ensure that the maximum transferred potential due to EPR is limited to less than 1200 volt. If the disconnection is more, of course, 250 volt, because the connected equipment cannot withstand more than this voltage. Now coming to the high voltage distribution system, I'm sure a lot of you are using the IEEE standard, and most of you knows the definition of these parameters. What is GPR, ground potential rise, which we in the IEC standard say EPR, earth potential rise, which is nothing but the UE, which is the normal, which is the new term, or the term actually used in the standard. UE is the earth potential rise, which is equal to ZE into IE. ZE is the impedance of the earth electrode. IE is the current which is flowing to the earth electrode. Please note that fault current is different than fault current. IF is different than IE, because the systems has to be designed in such a way that majority of the fault current must return back to the source through some kind of metallic fault return path, example an earthed conductor, or the shielding or the armoring of a cable. These are there in the regulation. I will show you. As a result, the earth current, the IE, is limited to a low level. As a result, UE is also limited and people are safe. That is the whole phenomena. The same figure from EN 50522. Exactly what we are talking. As you can see here, there is a transformer, there is a fault. S1, S2, R3, S3, these are called as potential grading electrode. Potential grading electrode, example, a ring earth electrode connected to the earth electrode E. So basically there is a fault. The person who is touching, you can see here UVT is the touch voltage and the example of a step voltage. All these are explained and the voltage gradient UE are explained in this particular figure. What is the limit of touch voltage? Yes, of course, it is given 1 second. Maximum touch voltage here, touch voltage, maximum touch voltage is 115 volt. Now to reduce the touch voltage, what we should do? S1, S2, S3, which is called as the potential grading electrode. On the other side of the transformer, a person who is standing and touching, you see the touch voltage is very high. He will get electrocuted. Whereas with the use of S1, S2, S3, which is called as the potential grading electrode, the touch voltage is limited to less than a safe level. You see UVT. Now, what is this EPR and in how much distance the EPR is limited? If we calculate based on the IEEE 142 standard, for example, so here in this graph, what you are seeing is the UE, which is the maximum EPR. And you have two cases. A means one earth electrode, maybe a vertical rod, and maybe multiple, maybe three earth electrodes, 3 meter deep, 15 millimeters dia, and 3 meters apart, 3 earth electrodes. So in both these cases, you see here are the distance from the earth electrode outside. So 10 meter away from the earth electrode, you can see almost 0.5 or 0. Case A, almost 0.5% of the stress is still applicable. Now, if we, from this particular graph, you can find this graph in the standard. If we apply 1 second disconnection time, in case of a single rod, 73% of the EPR gets reduced at a distance of 1 meter. Means if your touch voltage is, if your UE, EPR or GPR is 5 kV, touch voltage at 1 meter distance is almost 73% get reduced. That means from the exposed conductive part of the transformer to the place where you are standing 1 meter away, the potential difference is something about 3650 volt. Please note that this is applicable EPR of 5. If you use 2 earth rod, then this voltage is little bit less because the voltage is transferred. Is this the solution? Absolutely no. Dominic sir, am I audible? Because I get a message saying that the internet is not.
There is slight echo in the background. You're
Okay.
very much audible, but there is echo.
Okay. I think I cannot help echo, but
no, in that mic goes on the right. When you go to mic, click there. That says noiseless. Some feature is there to reduce the echo, but doesn't matter. You're very clear in what you're saying.
Okay. Let me check whether I can do. Probably we can do it later. It will be too.
Okay. But it is audible, sir. It not.
Okay. Now this graph, whatever I have seen, I have shown you this graph. Yeah, these voltages. You can also find more information in
miscommunication item. Again.
Hello, somebody is talking.
Sorry.
Yeah. So now you can find this information in IEEE 142 as well, where this kind of a figure is given and an example of calculating the earth electrode and how much the percentage of earth electrode resistance influenced over a distance. So you can find this particular information, approximate percentage of earth electrode resistance over a distance. With almost the same method, if we calculate or if we simulate or if we calculate, For example, if you have a single earth electrode where the UE is 5 kV, means IE into RE is 5 kV, the touch voltage is something about 3650 volt. If you have 3 earth electrodes, then it's 2900 volt and so on. So please calculate, look at IEEE 142 and calculate it. Now, what the regulation says. The Central Electricity Authority measures relating to safety and electric supply regulation 2023, also from the previous regulations, chapter 3, general safety requirements, regulation 18. Sub-regulation number 1. The supplier shall provide and maintain on consumer's premise for the consumer's use a suitable earthed terminal in an accessible position at or near the point of commencement of supply. So the sub-regulation is crystal clear. The supplier shall provide and maintain on consumer's premise for the consumer's use a suitable earthed terminal. So it is the responsibility of the supplier to provide an earthed terminal. Now, further explanation on this earthed terminal or continuity conductor you can find in regulation number 74, which says up to 33 kV along the overhead line, there has to be a earth continuity conductor as well, which is one side of the earth continuity conductor connected to the neutral of the transformer, the other side connected to the earthed terminal. I have a picture, I will show you. Regulation 50, sub-regulation 1 and the sub-regulation 1.1 limit the touch and step potential to tolerable values as per the relevant standard. So the first requirement is touch and step voltages must be lesser than the recommendation in the standard. The reason is people or animals should not get shocked. People should not get shocked. Of course, not animals. People should not get shocked. That is the first requirement. Second requirement. Limit the earth potential rise to tolerable values as per the relevant standard so as to prevent danger due to transfer of potential through ground, earth wire, cable sheath, fences, pipelines, and or other such equipment. Means the earth potential rise, UE or EPR, has to be limited in such a way that on the low voltage side, transfer potentials are limited. Number 1 example of transfer potential is the voltage which is created due to the fault in the high voltage system is destroying the equipment in the low voltage side of the transformer. Example, 25 numbers of or refrigerators in 25 houses burned, mixer grinders in 50 houses burned. So that is the second one. Limit the earth potential rise to tolerable values as per the relevant standard so as to prevent danger due to transfer of potential is the second requirement of the regulation. The third requirement of the regulation is maintain the resistance of the earth connection to such a value as to make operation of the protective device effective. You see, effective is very important. That means whatever the value you are getting should be stable. You set the relay on a stable value, means the earth system, including the connections, the values of the RE or other, the return path should not change based on the climatic conditions. Example, the earth electrode resistance is on dry condition, it is 10 ohm. During rain season, it is 2 ohm or 3 ohm. Such changes should not happen, or such changes should not affect the disconnection operation of the protective device is the requirement of the sub-regulation 1 of the regulation 50. So the regulation is very clear and it is the best regulation, I would say. Limit the touch voltage. The first sub-regulation, nobody gets shocked. Second sub-regulation, nothing in the consumer premise or nobody in the vicinity get a shock during this time, and maintain the resistance so that the protective devices are operating properly. If we put these regulations in a pictorial form, you will find this one. For example, for the picture, I am only showing the transformer, only secondary is shown for explanation. Only the star, the secondary winding of the 11 kV or 33 kV source is shown for the explanation. Then there are 3 lines in the distribution. Actually, it's not 3, it is 4 metallic wires, L1, L2, L3, and the continuous earth wire, which is called as earth conductor in regulation 74. regulation 17, regulation 18. This means if you have an overhead line from the substation to the origin of installation, means imagine in a consumer premise you have 11 kV 33 kV transformer up to the consumer premise, there must be a continuous earth conductor, which is a requirement of the regulation 74, regulation 17 and 18. The earthed neutral of the star connection, any system which you are using, the star point has to be earthed. This is in the regulation 50 sub-regulation 2. In the distribution, the earthed conductor also to be earthed, which is in regulation 74 1 sub-regulation A. No cutout link or switch shall be included in the earthed conductor sub-regulation, regulation 17. Like this, multiple regulations are require several requirements. Here, what I am saying is, for example, the secondary side of a source which is feeding 11 kV to 33 kV power to a transformer. Example, in a consumer premise, this also can be a transformer on the roadside which is feeding low voltage supply to multiple houses. So basically, if we look at the regulation, there must be a continuous earth wire. In case of an armored cable, there is a shield wire. There is not a shield wire, there is armoring for metallic fault return path. Now, in this particular, how can you calculate the short circuit current? The short circuit calculation line to earth, the short circuit is used, not fault. Short circuit in the sense it is a line is in touch with a metallic part. So there is the impedance considered is 0. The impedance of the fault is considered 0. So it is told as short circuit. The IEC 60909 part 1, part 3 explains various methods for calculating the fault current, the impedances of the fault return path. For example, I am just explaining you. There is a transformer. Here there is a station number 2. There are 3 single core cables. This is an example. Please note, this is an example. 3 single core cables. There is a fault on the station number 2. IK is the peak short circuit peak fault current. A portion of the fault current will flow through the shield which is connected from station B to station A. This is station B. This is station A. So through the shield wire, majority of the fault current is flowing. A portion of the fault current is also flowing through the ZE. ZE is the impedance of the earth electrode in station B. ZE is the impedance of the earth electrode in the station B. So basically, the total fault current, a portion of the fault current goes through the metallic fault return path and a portion through the earth electrode of both the stations. So this is the only case, this is the only opportunity. Imagine, just I'm explaining an example. I will show you where you can find such information. Imagine the fault current is 5 kiloampere. The ISA, that means the current which is flowing through the shield conductor is 4 kiloampere. Just for explaining to a normal, not a highly technical skilled engineer, I use the word IPE because in a lot of our presentations, we also use, for low voltage, we use the word IPE, the current through the earth, protective earth conductor. Imagine that from station 1 to station B, there is it's an overhead line and there is a earth conductor. Then through the earth conductor, a 4 kiloampere current goes and about 1 kiloampere goes through the ZE. That means through the earth electrode. This is just an example. Now the problem is, if there is no metallic fault return path, means if you are violating regulation 18 and regulation 74, fault current will flow through the earth electrode. There is only one route for the fault current flow. In this case, IE will be much lower than we expect. This is just a statement. Now, 60909 part 3, there are examples given calculating different methods. Say, for example, 110 kV, 110 kV substation. The secondary is 11 kV. 11 kV is fed to a transformer. There is a fault. I double dash means the fault current, the peak fault current. Then through the shielding, you can see here ISA, a portion of the current returns back because underground cables are used. Of course, for example, in Ahmedabad, the 11 kV distribution system, it is a solidly earthed system, underground cable. The cables are connected, both the armoring is connected at both the ends of station A and station B. As a result, the majority of the fault current will flow through the armoring, which is one of the best system, I would say. Now, the idea is the same standard. If you go through the annexures, you will be able to find out the examples. Say, for example, if you have a cable length of 5 kilometers, how much current is going to flow through the shield? How much IESA means how much current is flowing through the earth electrode? 10 kiloampere between station A and B, how much current is going through the earth electrode? How much current is going through the the shield wire? All these are very well explained. So what I wanted to tell you is, one mistake which we always try to do is, we calculate the earth grid or earth electrode assuming that the fault current is 13 kiloampere, fault current is 50 kiloampere, fault current is 25 kiloampere, and so on. In practical case, the earth electrode current, that means IE, is not that high. It is always very small, probably of the range of 1, 2, 3 kiloampere. It is never 50 kiloampere because majority of the fault current is supposed to flow through the metallic fault return path. Now, as an argument, if somebody want, we can go to the standard 60909 and part 3, and we can have a detailed calculation and find out what exactly are these values. Now imagine a perfect electrical installation, a perfect distribution system, starting with a source 11 kV, 33 kV at the secondary side of the transformer, maybe the primary is 66 kV, for example, and which is feeding to a 11 kV, 33 kV bar 400 volt transformer. You have the 3 lines, you have the earth wire as per Revelation 18 and 74. Imagine there is a fault, IF. IF stands for the fault current. IPE I put just to, as I said, I am putting this value. It is, you cannot find IPE in the high voltage standards. I am putting it just to tell you that there is an earth conductor, protective earth conductor, because we are explaining too much on the low voltage side and a lot of people know what is PE. So there is an earth conductor. A portion of the current will flow through the earth conductor IPE, and a portion of the current will flow through IE and ZE. So what I have put is IPE equals IF, means the total fault current, minus IE. So IF, the total fault current, IE goes to the earth electrode, IPE goes through the metallic fault return path. Now what you must calculate is the UE, the EPR at ZE, which is IE into ZE. Example I am just putting. The following could be an example of fault situation. I have taken a very high level of fault current, 10 kiloampere, which is most of the time practically very high. IF, just for your information, let's say 10 kiloampere is the fault current. IPE, actually it's ISA. IPE, imagine it is 9 kiloampere. The current through the earth electrode is 1 kiloampere. Imagine the impedance of the earth electrode is 1 ohm. Please note that this is an arbitrary value. Just for explanation, I am taking 1 ohm. Don't think that 1 ohm earth electrode resistance is required anywhere. No, that is not a requirement. Now, under this condition, the total voltage gradient or EPR is something about 1000 volt. 1000 volt is the EPR. The applicable touch voltage to a conductive part at consumer premise. Consumer premise means the transformer, 11 kV side of the transformer at a distance 1 meter will be approximately 500 to 600 volt. So once when the transformer body is 1000 volt, a person who is standing 1 meter away will experience a shock voltage, touch voltage of up to 500 to 600 volt. The idea is maximum 1 second disconnection time, this voltage is 115 volt. The touch voltage is higher than the tolerable limit for 1 second disconnection, because 1 second disconnection, that is the touch voltage is less than 115 volt. And this is within the tolerable limit for 0.1 second disconnection time. For 0.1 second, the touch voltage 100 millisecond, if the circuit breaker is tripping in 100 millisecond, the touch voltage is something about 660 volt or even a little bit higher. So not only the touch voltage, the disconnection time also plays a major role here. But what I wanted to explain you is if you are following the regulation 18 and regulation 74, majority of the fault current goes through either the armoring or through the metallic fault return path. Only a very less amount of current flows through the earth electrode. As a result, the earth potential rise is very much under control. Chance of people getting shock is very much under control, very much limited. Now, if we look at the standards, any Indian standard 60909 or any of the international standard, there is no system explained without this IPE. That means without a metallic fault return path, there is no system explained. Why I made this statement is, in India, if we look at some of the states, I won't say all the states, some of the states, if we look at the 11 kV distribution on the roadside, you will see only 3 lines, RYB. The fourth wire is totally missing. There is no continuous earth wire, which is a violation of regulation 74, regulation 17 and regulation 18. So basically, no continuous earth wire in an overhead line is a violation of the regulation. So under this condition, what happens is the terminal which is at the consumer premise, let's say 11 kV consumer, the terminal at the consumer premise, you cannot call this an earthed terminal. You can call this terminal as an earthed terminal only if there is a continuous earth wire. Now there is no earth wire. You are just having an earth electrode and connecting. Under this condition, this is a violation of this earth terminal. This terminal is a violation of regulation 18. So basically, continuous earth wire, if continuous metallic fault return path is missing, for any application above 1 kV AC, it's a violation of the regulation. It's also a violation of the available standards so far. What I am saying is, all the available standards and regulation explains a system with a metallic fault return path for application above 1 kV. This is not new. These are there in the regulation since decades. These are there in the standards since decades. Under this condition, imagine there is a fault, IF. There is no metallic fault return path, so I put IP as 0. The entire IE equals IF. IE means the current which is flowing through the earth electrode is the total fault current. Of course, there is inherent resistance of the earth electrode which is at the location B and inherent resistance of the earth electrode at station number A. These earth electrodes, since the current is flowing through the earth electrodes, the fault current IF itself will be very much reduced. It will not be like, 10 kiloampere, 15 kiloampere is never going to come. It will be a much lower value. I just put a very small arbitrary value. Imagine an installation without metallic fault return path, and imagine the fault current is 3 kiloampere. So the current through the metallic fault return path is 0. IE means through the earth electrode, 3 kiloamperes of current is flowing. Imagine the earth electrode resistance is 1 ohm, the voltage gradient, the potential gradient EPR, earth potential rise is almost 3000 volt. This 3000 volt is much multiples of times more than the tolerable limit, because the tolerable limit in case of 1 second disconnection is 115 volt, 0.1 second disconnection is about 600 volt. So under this condition, without a metallic fault return path, or wherever you are violating regulation 18 and 74, the 11 kV side of the transformer will have a touch voltage much higher than the tolerable limit. Now I am showing you a transformer. Imagine this is a 11 kV bar 400 volt transformer. The 11 kV is connected to one earth electrode, maybe a pipe or a plate. The top view, something it looks like this. There is a transformer. a wire connected to the earth electrode. During an earth fault, UVT means the tolerable touch voltage, which will be much higher than the tolerable limit. The actual potential which is created, actual touch potential in this area will be, example 3 kV is the UE, then the touch voltage may be about 1500, 1600 volt. A person who is standing there and touching, he is literally, he is dead because the touch voltages are much higher than the tolerable limit. So here you can see the definitions of these words, UVT, UTP, and so on. UTP is the permissible touch voltage. It is the maximum limit of the touch voltage. UVT is the prospective touch voltage, which is the voltage between simultaneously accessible conductive parts when those conductive parts are not being touched. So basically, the tolerable limit, the prospective touch voltage is much higher than the tolerable limit. As a result, people get shocked. Conclusion. Using plate, rod, or pipe electrodes for high voltage side of the transformer earthing transformer is dangerous in location where regulation 18 and 74 are violated. What is regulation violation of 74 and 18 and 74? The violation is there is no metallic fault return path. The earth wire, the continuous earth wire itself is missing. Under that condition, for the high voltage side of the transformer, if you are earthing it through a pipe or a plate or a rod, you are actually in danger because the tolerable limit of touch voltages will be, UVT will be much higher than the limits. So what do we do? The only example or the only possible solution is to have a potential grading. Example of potential grading in a building. This picture was a part of the last National Building Code of India, but however, I think it has been, I can't find it. But anyway, this is what is explained as potential grading. Potential grading, as you can see in one of the previous slide, I have shown what is potential grading. Let me show you that particular figure as well. Potential grading. Yes. Yeah, in this figure, you have seen the S1, S2, S3. This S1, S2, S3 is the potential grading. S1, S2, S3, potential grading earth electrode, a ring earth electrode connected to the earth electrode E. That means they are connected to the earth electrode and to the body of this particular transformer. So basically, potential grading means all around that particular installation, say for example, 1 meter away from the installation, let's say 1 meter away from your transformer, 200 to 300 millimeter deep, you should make a ring, the ring number 1. The second ring is again 3 meters from the first ring, 700 to 1000 millimeters below. The third ring, again 3 meters away from the second ring, 1200 to 1500 mm below. So basically, by this method, we are supposed to calculate the grading rings, and we are supposed to install grading rings all around the transformer in order to protect people and the property, or in order to protect people from shock voltages. So an example, something like this, as I said, the first ring is maybe 1 meter away from the transformer, but 200 to 300 millimeters below. The second one is 3 meters away from the first ring, 1 meter below. The third one is again 3 meters away from the second ring, again 0.5 meter below. So basically, this is the way voltage grading has to be carried out, as you can see in this particular picture. So you see here S1, S2, S3. Now, conclusion. The simple conclusion is, why I am making this strong statement is, we always have the habit of using plate calculated for some fault current, 13 kiloampere of fault current going through the plate. You need 23 plates in one case, maybe 15 plate in another case, 2 plate in another case where the soil resistivity is very low. Using plate, pipe, rod in HV side of the transformer is dangerous in locations where regulation 17 and 18 and 74 are violated. As a result, means since you are violating regulation 18 and 74, regulation 50 is also violated because there is no metallic fault return path. UVT will be much higher than the tolerable limit UTP. As a result, people get shocked. Potential grading calculated based on soil resistivity and fault current are necessary to comply regulation 50. So, the last part of my presentation today, using plate, rod, pipe electrodes of high voltage transfer for the high voltage side of the transformer is dangerous in locations where these are violated. In multiple states, in several states, these regulation 18 and 74 are violated. Using plate, rod, pipe electrode, as stated in the conclusion 1, regulation 50 is also violated. In all case, potential grading is the only solution to comply regulation 50 subregulation 1I. Global earthing system with foundation embedded earth electrodes in industrial and commercial premise can comply regulation 50 subregulation 2 and 3, not 7. This is and without seasonal changes, because if you go for foundation embedded earth electrode, it is not influenced by the seasonal changes like, dry season, X value, wet season, Y value, and so on. So basically, my recommendation is never ever try to violate or follow the regulations strictly. The regulations and the standards are made with a lot of information, lot of experience, lot of safety measures are thought of, and these are made. Please never try to compromise or never try to violate the regulation. Violating regulation 74, 18, and 50 is a dangerous situation. People and animals, living beings get electrocuted. As a result, whenever there is a fault, people will die. So this is what I wanted to explain in today's presentation. Thank you very much. Over to you, Mr. Dominic. We can have a question answer.
Yes, sir. So we have, I request the participant to post your question answer, but it should be related to today's topic only. Please do not deviate the subject from today's topic. So I will just take the first question, sir, from Gaurav Mishra. What is the right method of neutral earthing in parallel operation of HT generator?
Neutral earthing in parallel operation of HT generator. I think he's asking about neutral earthing of a transformer in a HT. Sir, very easy. There in IS 3043 there are some figures. I hope the figure is 44, 45. Please have a look at the figures. There it is explained. 44, 45, 46. I think. Probably, if you are interested, I can show the figures. Just a moment, please. Let me open the standard.
Okay. While he's talking, Akanksha Rao, I know you're a student. I would request you to become a student chapter. Then you go to internship. There are a lot of opportunity for employment within our members. So I would request you to become student chapter. We're doing a lot of internship also. You're most welcome. So I'm just, since you're a student, I'm just guiding you on this. Okay. Amrit Lal is asking, common failure over voltage is because of failure of
Sir, can we answer the first one and go to
yes,
this
sir.
one?
Go ahead, sir.
Okay, now I am showing the single high voltage standby generating set not suitable for parallel operation. That means the HT generator and the supply with the manual changeover. The next picture, single high voltage standby generator set suitable for parallel operation with incoming main supply. That means the main supply and the generator is synchronized with NGR, without NGR. So you can find this information from these figures. Figure number 43, 44, 45. Also 46. So I recommend you please go through these figures and get the answer, please.
Yes, sir. So I'll take the question from Amritlal. Common failure over voltage is because of failure of neutral. The voltage shifts according to the load current. I don't know whether Amritlal is answering.
Yeah. I don't know whether it's a question or because it's an answer. Yes, of course, if your neutral gets disconnected, the connected equipment between the live conductors, instead of 230 volt between line and neutral, maybe 440 will come and the equipment gets buggered. So you are not supposed to fail the neutral under any condition. So you have to make the installation in such a way that the neutral is in firm condition always. Why does it fail? If you make a mistake, if you make a loose contact, or if you make a joint, probably it fails. Also, if we go through for low voltage system, if the recommendation like the TNCS system,
Sir,
PME,
in case of residential with 3 to 4 story building in which there are many equipment like transformer, DG set, lift, solar, UPS, how much minimum earth pits can be planned due to space constraint? This we've been talking in almost all the workshop. It's talking
yes,
multiple
of course.
earth pit that is looking.
So what I recommend is, I recommend the users to go through. Let me show you the technical.
Sir, you're on mute. We can't hear you.
Am I? No, it's not mute. I'm not mute. Can you hear me? Hello?
Yes, sir, we can hear you, sir.
Okay.
Yeah.
So I got confused. One
Now I
moment. Let me open the. Please note that we are publishing a lot of documents. We have published a guide on regulation number 43. Let me show the guide, which is available in our website. Initially, we made it free for our everybody to see, but now I think we made it only for the members. So all NFE members can look into this particular guide, where the answer for the question is explained. In a building, residential building, how many earth electrodes are required? I would recommend the gentleman who has asked to go to National Building Code of India. You download the National Building Code of India or IS 732, where you can find this particular picture, how to make earth electrode in a building. I think a better picture is also there. Yeah, both in NEC as well as IS 732, you can find this kind of a picture. So I would recommend you please go through and for your question, how many earth electrodes, if you are asking about vertical rod or pipe, I would say 0. You don't need a pipe or a rod in a building. You can make use of the foundation steel, which is called as foundation embedded earth electrode.
Sir, Dhananjay Wag is asking, what are the possible practical ways to limit the touch voltage?
Yeah, this is what is explained in the final slide. It is to make voltage grading rings all around your installation. As a result, potential step and touch potentials are under limit.
I'll take Anil Kumar. Will continuous earthing connectivity is applicable for underground cable connection system also? At site, usual practice is to leave anyone in any one end of cable armor in open condition to avoid circulating currents.
Actually, this is a misconception. First of all, at both the ends, you must terminate the armoring properly. As a result, there is a metallic fault return path. The techniques to avoid the circulating current are different. First of all, there should be sufficient insulation. And in a 11 kV or 33 kV side, the chances of a circulating current is quite less. There are documents explaining this particular thing, and very easily we can avoid leakage current. But don't avoid this metallic fault return path, which is actually a bigger problem in case of a fault.
Sir Deep Shah, what is our newly appointed Gujarat chapter president? what if transformer is installed on slab for potential gradient ring?
Yes, all around the slab. You have a RCC floor for your transformer. All around the transformer on the soil, you have to make voltage grading.
So Gopal Singh Yadav is asking 132 and 33 kV substation grid earth value is 2 ohms. What will be change in touch and step potential voltage?
Yeah. With respect to touch voltage, irrespective of voltage, if first is what is your disconnection time? If it is 1 second, 115 volt, 115 volt is the touch voltage without for a person without PPEs, without any additional resistance in hand or in shoes. So then for your question, we have to really calculate how much current is flowing in the earth electrode and find out the touch voltage.
Rajendra Singh, how to make return path if armored cable is earthed at one end?
You have to earth at both ends. You see, to solve one problem, we are ending up with another problem. Armoring one end is not the correct solution for circulating currents. Yes, of course, it depends on the situation. There are, if you have an earthed system, unearthed system, or a system earthed with a high impedance, then of course it varies.
So Prudvi is asking, please explain about neutral earthing. Is that possible, sir?
Neutral earthing is called a system referencing earthing. Electrical installation, in order to limit the insulation of the conductors to earth, it is a practice to earth one of the current carrying conductors to a reference, that is neutral earth. Conveniently, we take the star point and earth it, which is called as neutral earth.
So Rajan Menon is asking, do we need continuity required from 110 kV transmission to 33 kV distribution, a solid earth continuity required?
Yeah, if you don't have, then it's you are violating the regulation.
That's right answer. So Manoj is asking, please advise the switching surge and high voltage safety for ST panel and transformer.
Probably we can take it up in another webinar.
Yeah.
This will be.
Switch surge and high voltage safety for ST
I
panel.
request participants to be specific on the subject. So the other subjects we can take up separately.
Okay, can you explain? Or would you like to take the question that is relevant, sir? Because I cannot be
Yeah,
that will
Mr.
be
Imran is asking, can you please explain how this grading helps in reducing stress voltage in LT side and protect our appliances? Of course, the grading electrode will not have any influence on the LT side of the transformer. So handling the voltage stress on the low voltage side is a different method. That is why in the conclusion I made for for the stress voltage at the LT side, you need to have a TNS system at the LT side. So where the HT and LT are connected together, and protective equipotential bonding at the consumer premise. Probably this we can explain. This is already explained in multiple of our webinars. So basically, voltage grading is only to reduce the touch voltage of that location. It is not going to have much influence on the low voltage side of the transformer. So, sir, now the next question is from Mr. Sanjeev Kumar. We are using 132 bar 11 kV star transformer with a neutral of LV side grounded through NGR. What will have effect on current magnitude through the metallic fault return path? Of course, in case since you have an NGR, the earth fault current is very less. The intensity, the amount of earth fault current is very less. But you need to have an increased insulation for your cable. So there is a question from an anonymous attendee. Since we do not have any control on utility as well as any maintenance step off that may take place upstream, is always necessary to assume that there is no metallic earth return to be safe. and be safe even if we have one. Of course, the question the person is asking, we always, the utility is not providing any earth conductor. So what do we do? Sir, this is not correct. Not always. Majority of the cases, probably there is no fault return path, but a lot of utilities are providing metallic fault return path. So if it is violated, then of course you need to make the necessary measure. For MSc, Aishwarya Sawant is asking, for MSc DCL, we are getting 11 kV 3 core 300 square cable consumer underground earth. That means it is a violation. You are talking about the current carrying conductor. You are not talking anything. Your question is not clear on the return path. So probably we cannot answer this question. Is it necessary to have continuous earthing conductor in case of 11 kV to 400 volt system? Of course, the recommended system is 11 kV, the high voltage and low voltage system, interconnected system. In the low voltage side, we are supposed to make a TN system where there is a metallic fault return path available. In the 11 kV also, there is a metallic fault return path available. That is the best way as far as safety is concerned. Dominic sir, Apav sir is on the line. Can we take it?
Let's check, sir.
Okay. Mr. Chidambar Joshi is asking a question. Since we do not have any control on utility, okay, now I think this is the same question which I already answered.
Sir, Apav sir, you are there on panel, sir.
So Mr. Amritlal is again, I don't know whether it is a question or a statement. Mr. Amritlal, if there is a statement, probably you can put it on the chat box. So if there is a question, let us limit the Q&A with the questions. Oh, again another question from iPhone. Early streamer emission or conventional type, which one is best?
Hello.
So,
Hello.
Then,
Sorry, I just joined as a panelist. I am on a travel, but I could say that it's a good start because there are no standalone LV installations. They are all connected to the HV side only. So I have to take into account of the temporary over voltage from the HV side, for which the interconnections are most required. However, there are no overhead screen wire up to 33 kV. This cabling is available in urban areas, urban cities. In most of the rural sections, only 20% of the distribution is covered in the urban cities. Most of the 80% installations are rural areas where the problem occurs, where 11 and 33 kV lines are there without overhead screen or continuous screen on the HV side. We can have it on the LV side, but not on the HV side. So this is the problem. We have to mitigate this problem by addressing specific ways. Because in the absence of HV earth screen for such a distribution, you can see the table of IEC 61936 part 1, where the stress voltage and consumer side touch voltages are very high, but it's not shown in TT system. So that's why in the TT system, the touch voltage is limited because of the ground impedance, higher ground impedance. Whatever the fault current we calculate is not taking into account of the TT, because the earth resistance drastically reduces the fault current, especially in TT system. That's why in the LV distribution, in the absence of a continuous earth wire and HV earth screen, etc., we do have a sufficient amount of additional impedance. So that's why people are hesitant. We can't blame people. They are hesitant to provide their PE conductor with the suppliers conductors. So this is an issue we have to take up, I think, in the other webinars. A good start, I can say. We have to take up
Yeah.
this
Sir,
subject
sir,
of touch
Above,
and
sir.
step potential that we going to resonate. That's what I
Above,
say.
sir. Above,
Thank
sir,
you.
one question. I would like you to answer one question. In IS 30, can you hear me?
Yes, sir. Yes, sir.
Yeah. In IS 3043, somewhere in the regulation, it is written as the assumed fault current should be 13.1 kiloampere. What is your opinion on that? And the earth.
13. Yes. See, not only this 13.1, there are several arbitrary values taken. 50 kA for 230 kV substation and 13.1 kA for such things. These are all never existent. These 13.1 kA do not exist in any of the 11 kV distribution globally. Actually, the CA regulation is not intended to take this value for earth fault. This is a value to be taken for sizing the gears, switch gears. For example, circuit breakers. The circuit breakers short time withstand capacity as well as the short circuit capacity should take into account of this fault current, not this for the earth fault or earth touch potential limitations. This difference we have to take into account, and we have to meticulously see the IES, technical regulations. It's clear. It insists for the breaker capacity only, not for the fault current for touch potential capacity. But people invariably take this. Okay, sir?
Yeah. Thank you. I think Mr. Rajan Menon is also there. Mr.
Rajan Menon,
Rajan,
you want to talk? You can unmute and you can speak to the speaker. Rajan Menon, can you hear me?
Okay, I think he's not there. Now the next question is from Mr. Anburajan. Why you are taking 3 kiloampere instead of 10 kiloampere for ground fault line in a line without continuous protective earthing conductor? Okay, the first point is, if there is no metallic fault return path, the amount of current which is going through the earth electrode is not like 10 kiloampere because you have the inherent resistance. In the previous case, I took 10 kiloampere, but 9 kiloampere flows through the metallic fault return path. Only 1 kiloampere flows through the earth electrode. In the second case, 3 kiloampere through the earth electrode because there is no metallic fault return path. You can calculate it based on the assumptions, based on the calculations provided in the standard. This 3 kiloampere itself is a very high value. The actual current in a 11 kV, 33 kV system through the earth electrode will be very less. It will be of the order of 1 kiloampere, 2 kiloampere. Again, depending upon the distance between the stations, whether it is 1 kilometer or 10 kilometer, then what kind of earth electrode is there, what kind of earth electrode resistance are there at the upstream as well as in the downstream. So there are several parameters which is influencing. I took an arbitrary value, as I said. Question from Mr. Mohit Kumar, is chemical earth pit allowed? Mr. Mohit, there is nothing called as chemical earth pit. These are some bogus things created and followed in the market. So don't go behind these bogus things. I will show you what is written and what has to be followed. The only standard which is requesting to put an earth enhancing compound, which we generally call as chemical, is in IS or IEC 62305, which is the lightning protection standard. Let me go to 5.4, earth termination system. 5.4 explains how earth termination system has to be made. Now, what is written? You see here, in soil with the resistivity higher than 3000 ohm meter, that means you are in a really rocky place. Type B earthing arrangement or earth enhancing compounds are effective. If you are in a rocky place and you cannot make a type B, that means mesh or ring earth electrode, then you can go for an earth enhancing compound. And these are sometimes called as chemical earth. Number two, in soil with resistivity less than 200 ohm meter, earth enhancing compounds are not effective. Means if you put it in a normal soil, 30 ohm meter, 50 ohm meter, if you put a chemical, actually the chemical corrode your electrode. So less than 200 ohm meter, it is not at all effective. You don't need to use it. So with soil resistivity, low soil resistivity, corrosion of earth electrode can be considered from this particular standard 62561 part 7, which is also an Indian standard now. So basically, if you put this chemical in the earth electrode, you are actually increasing the corrosion of your earth electrode. So if you have soil resistivity more than 3000 ohm meter, probably you can think of chemical. Otherwise, don't use it.
Rajan, are you there? Can you hear us? You want to speak?
I think no.
Okay, no, that you unmuted the mic, so I thought I'll
Yeah.
take it.
So we have Mr. Rahul Pal.
Yeah, Rahul Pal,
Okay.
would you like to? I have unmuted Rajan Menon. Please go ahead. You're unmuted.
I think probably there is some problem in his mic. So if he tried to speak, maybe it will be a.
Rahul Pal, would you like to talk to the speaker?
Okay, now coming to the other point, somebody is asking to share the PowerPoint. Please note that none of the PowerPoints will be shared. The video will be uploaded in NFE YouTube channel. You have to look at the video. So I'm so sorry that we will not be able to share the PowerPoints because these are made with a lot of effort. Then Mr.
Gayatri,
Srinivasulu.
there is one minute, sir. There's one more. Gayatri, ma'am, would you like to talk?
You have to
Rahul.
unmute yourself.
सर वॉइस क्लियर नहीं आ रही उतनी
No, अभी clear है, clear है. You can, because Mr. Gopakam may not understand Hindi, preferably in English. आप बात कीजिए sir, Rahul Pal. Okay, let's take the question, sir. We'll keep moving.
Okay,
Srinivas.
Mr. Srinivasulu, HT earth can combined with LT earth, of course. Combined earth is what is recommended in the standard. If you go for a especially TNS system, which is there, again the regulation 18 for low voltage side, of course HT and LT combining is the best method. So Motorola Moto, evenly distributed distance between earth electrodes and connected with each other, also connected between the earthing point. I don't know what happened, that question disappeared. Mr. Jaykumar is asking a question. In a long cable network with many cable joints, is the IF return path through the cable armor and shielding reliable? Is there any data showing that the integrity of the armor connection and joints is intact throughout its lifespan? Very good question, Mr. Jaykumar. Of course, in case of long cable network, the first point is the fault current itself will get reduced because of the inherent impedance of the cable as well as the return path. Number two, once when you are making a joint as recommended in the standard, of course, you can be sure that the joints are in very good condition for a longer time. You can also test these, continuity resistances can be tested if there are methods to ensure that.
Rajan, I want to talk again. You're coming again. The third time you're coming back. You want to talk? Please go ahead. Rajan
Now
Menon.
there is, Mr. Taral Patel who is asking what is the size of strip rod for ring around the transformer. Please have a look at IS 732 where the size of the earth electrodes are recommended. Then the question, how many rings are required? Here we have to really make a calculation. We have to find out the soil resistivity. We have to find out the earth current through the earth electrode. Then find out the GPR. Then find out the whole system. If you are not using global earthing system, I will show you what is recommended in the standard, both in the National Electrical Code of India as well as in the IS-IEC standard. Just a moment, please hold on, please. Practically, yeah, this is the standard 61936. Whatever I'm going to show, you can also find out in the National Electrical Code of India. Annexure, yeah, D. This is how we are supposed to make earthing. What are the steps to be followed while making an earthing system? More than 1 kV AC. Earthing system design flowchart. Data collection, initial design, global earthing system, yes, design complete. Means if you are in an industry or a part of a large building, then the recommended measure is to go for a global earthing system where LV, HV, ELV, lightning protection, everything is interconnected together. And global earthing can be achieved where the touch and step voltages are within the limit. Yes, design complete, very easy. If you cannot make a global earthing system, that means you have a standalone substation, which is maybe a part of a transmission substation or a distribution substation. Under that condition, we have to determine the soil characteristics. Current flowing to earth means how much IE, the earth electrode current going, determination of the RE, earth electrode resistance, how much GPR is created, whether the permissible touch voltage is lesser than the touch voltage. You see, compare the EPR and the permissible touch voltage. If it is yes, design complete. Or you have to follow this particular method and make grading rings in such a way that the earth potential rise both is within the tolerable limits of, or the step and touch voltages are within the tolerable limits. So this is the method. For industrial and commercial premises, the best way is to go for global earthing system. So I hope I answered your question. So Mr. Guru Prasad, in my
Is Gayatri, can you hear me? Gayatri, I would like to talk.
probably there is some issue with the mic.
Yeah, I think everybody seems to be having a problem with the mic.
Yes.
Amritlal would like to talk. Amritlal, go ahead.
Yeah.
Yeah.
Good morning. I think I'm.
Can you be louder?
Yeah.
Yeah.
The thing is, I want to tell, when we interconnect biconductors, the GPR on the primary side part of the source is going to create another voltage hike. Am I
You are
correct?
audible.
Yeah. Am I correct in that statement?
What is the statement?
Statement is, when you have a source and you have a load, consumer premise. On the source side, you have 110 or 66 kV. Usually
Yeah.
the transformers are on YN YN. It will be interconnected. So once you start a metallic proper connection, what you end up is the primary side 110 kV fault will be transferred to the
Today's our
consumer.
discussion, today's total webinar is on the subject of 11 kV and 233 kV distribution. Please restrict the
correct.
question to this and the LV segment.
Yeah, correct. That 11 kV is derived from one substation, which is 66 or 110. That is one point. Another point is, once you start interconnecting, your current is going to increase if you have metal part. It will not be like the soil where you have very little fault current. Once you start connecting with the conductor, the impedance is going to be the conductor resistance or the conductor impedance. So the fault current, we should have some value assumed, because you don't know how the system is going to grow. So the fault current is tend to grow. So we cannot arbitrarily take any value, or we have to have a value in the standards.
Okay, what is the question?
Question is, how do we fix up that? The
First of all, you
13.1
don't
is
need
the
to
present
assume.
one.
Yeah, first of all, you don't need to assume any values. There are very clear calculations. There are very clear standards where each and every part of the systems are very well explained and calculations are given. Instead of assuming something, it is always better to calculate based on the actual system. This is number one. Now, interconnection is the recommended method. You cannot really isolate in any of the place. What do you isolate? Neutral of the transformer? You don't need to. If you wanted to have a neutral isolated system, go for a the neutral isolation, maybe an NGR or maybe impedance earthed system. Other than that, all the metallic exposed extraneous conductive parts must be bonded is the best method. But still, I'm not clear about your question.
No, my question is about the current. I mean, the
Current will be
primary
high,
side of
of
the
course.
transformer of the feeding substation. You cannot have a constant current. And if you calculate for today, that may be changed tomorrow because the system is growing.
We are talking about earth fault current. We are not talking continuous current.
Yeah, I am talking about the fault current. Okay, anyway,
Sir,
we
we
will
have
talk it
59
later.
questions, so can we move forward, sir? Because we have very limited time.
Yeah. Okay.
Yeah, Bhushan would like to talk. You're on. You can unmute and speak to sir, because we have 59 questions. So let's go forward quickly. Bhushan, yeah, go ahead.
I'm not able to unmute.
Yeah,
Yeah,
no,
we can hear you.
Aja, is it? Okay. So, so the question is, in DISCOM, the common phenomena in distribution network is the insulator of HT line breaks, and sometimes even the jumper touches the 2-pole or 4-pole structure near the substation, and this leads to temporary over voltages even in LT network. How earthing can be provided, or earthing arrangements can be provided to protect such situations, or what measures can be taken in the switching station so that such incidents is avoided immediately, or a supply is disconnected immediately, not causing any disturbance in the LT network. Thank you.
Yeah. Thank you, Mr. Bhushan. The connected equipment at the LT network, in case of a fault due to a jumper, touching a live part or whatever you explained, there is a GPR created, and this potential will be transferred to the low voltage side of the transformer. If LT and HT side, sometimes if they are not interconnected, the winding will have stress. If they are interconnected, the equipment at the consumer premise will get this particular stress. So the solution number one is at the transformer, imagine 11 kV primary and 400 volt, 440 volt secondary. The neutral earthing of the secondary side can be made far away, maybe 15-20 meters away from the substation, away from the metallic parts, including earth electrodes of the substation. This can avoid transfer potential, but there is no conclusive solution. If you solve one problem by a technique, then you will end up with another problem. So the best method for this question is you go to the IS 732 clause 4.5, where this this method, the entire method of solutions are explained with a simple picture with calculations. We made a webinar long back. If we can find out the link of that webinar, the entire answers are there in this webinar.
So if all the members, the NFU member can access to those webinar that there in the website. So Rajkumar Velu is asking electronic earth pit for PLC system panels and electrical earth pit for LT MCC should be separate or not?
Dear Mr. Rajkumar, there is nothing separate. All the earth electrodes are connected or they are connected through the mother earth. So you cannot really separate. If you wanted to separate, put a separate pit, then we have to make it really in the moon. One in the earth and one in the moon. Then we can say that these two are electrically separate. Otherwise, it's impossible. So the best method is you must interconnect, and there is no need for this separation. These methods you can find in IS 732, again clause 4.5.
So Lakshmisha is asking which standard can be referred to know about interconnection of earth pits?
Actually, the answer is a little bit tricky. In no standards, you can find earth electrodes to be separate. All standards, you can find only interconnected earth electrodes. I hope the answer is clear. The answer is all standards and all regulation.
So Jay Patke is asking, in regard to stress potential, HV or LV during HV fault, my question is that the precaution mentioned in today's webinar about touch and step potential, does it also take care during lightning strike as well? And we do consider it as fault or some other scenario which need to be addressed using some other method.
Yeah, the answer is to some extent. I cannot conclusively make an answer to this. To some extent, then the question is what kind of system are we talking about? Whether is it a part of a building or a standalone transformer? So all these questions need to be considered. So there is no answer for this particular question because the subject itself is a different subject.
Again about earth pit, is it okay to connect MV earth pit and LV earth pit together and make single grid? Can we connect neutral earth electrode to connected with earth grid, or should it be separated? Again, the
So
same question.
the recommended method is connected together. Means the body of the transformer and the neutral of the same LV side of the transformer, both can be connected to a common bus bar.
Sir, since we have another 59 question, can you pick only another 2-3 questions so that we can answer to them directly through the mail? Later we can do that because there are 59 questions. I don't know which is the right question that is relevant for people who are listening, because still there are 300 people waiting, listening to the question. So can we pick up some interesting question that you find it, sir?
So how many questions we can answer? 2? There
Well,
are
let's take
59.
let's take 3 questions, sir.
Okay. So let us take one from middle, one from maybe the last end. Okay. So many anonymous. Most of the questions I am also unable to understand. Can we loop one of redundant neutral conductor of transformer earthing with the body earthing terminal? Can we loop one of the redundant neutral conductor of the transformer with earth? I don't understand this particular question. I am so sorry. Again, I think not a lot of anonymous attendees. Anonymous attendee, as per my interpretation of regulation 18 of CEA, TT system shall not be used. Instead, TNS or TNCS earthing system shall be used. Actually, CEA is encouraging to adopt TN system. Am I correct? 100% is, sir. The CEA is never ever considering TT system, because when the 1956 IE rule is made, or before that, once when the 1937 electricity rule is made, at that time there was no TT system. There was only TN, either TNS or TN, only TN system was existing. Even today, the regulation has not changed. The regulation is pakka on TN system, but the users are making sometimes the mistake. Now, Mr. Kiran Joshi is asking, for India perspective, we find everywhere TNC network. Is it really safe, or every time we need to convert to TNCS network? Mr. Kiran, within the consumer premise, we must follow TNS. The supply can be TNC outside. That is up to the point of commencement of supply. But within the building, it must be TNS only. So now, most of the accidents a lot of accidents in our network are due to using TNC within our building, which is actually a violation. In several standards, it's very clearly written not to use TNC because it's a hazard. Don't use it. TNS is the best. Means a 5-wire system. So, sir, again, lot of questions. I'm trying to find out one question. Electrical inspector asked for, from Mr. Balu, electrical inspector asked for separate earth pit for transformer, transformer neutral body, etc. Is it really required separately? Sorry, it is not really required. If you, what you can do is you can take again IS 3043, for example. So I have referred some figures 41, 42 and all. You go to figure 38, 39 and 40 and all. So there it's very clearly the figure explains the body of the the DG and the neutral of the DG must be bonded to the common bus bar. Let me share it with you. I hope this is visible. Yeah. You see here figure number 38 of IS 3043. Of course, this is not for transformer, but for a DG with mains. You see there is an earthing bar. The body of the okay, this is 39. Okay, this one. The body of the DG, including engine alternator and the neutral, both are connected to a common bus bar. This is the correct method. The same method can be followed for transformer as well. So that's all, sir. We answered three.
Yeah, I think still audience are waiting, but unfortunately we are exactly 2 hours since we started this program. Look like that a lot of interest has been created in this subject. We may have to continue this webinar in different series to very specific, the needs. The questions that has come in can help us to come out with another series on the same subject. So, as I said, we have a couple more webinars coming up. We have already mentioned that one on the green wire, fire resistance cable. Then about switch RC, type B RCCB. So we have a couple of more coming this month in March. Keep tuned and keep looking at our communication, so you'll get received this, and we'll try to answer as many questions that has come in possible. But Sir Gopakumar's office will reply to you. I would urge everyone to become a member so that many of the 90% of the questions are already answered in our previous webinar. So if you get access, you can get access only when you become a member. So it's very simple, around 1,700 rupees an individual member. So I request once again you to become a member of NFE. So thank Mr. Gopakumar for having patience with a lot of
So you
questions
can
coming
also,
in.
sorry to disturb you, you can also forward the link for joining as an NFE member so that it is easy for the
It has been sent, Lakshmi, since you are doing the backend, did you send the link to become a member?
I am also
Yes, sir,
sharing my
it's done.
screen.
Yeah.
I am also sharing my screen just to show the participants that a lot of questions which is there. We had about, I think about now 70 questions are there. Most of the answers for the questions are available in our guide, Understanding Regulation 43. No, almost most of the questions which I can see on the Q&A are answered in this particular our book. I request you please download the book and read it. Of course, I think we made it only for members, for NFE members. Thank you. Over to you, Dominic, sir.
Okay, thank you so much. There are a lot of congratulatory messages that we are getting for conducting very useful webinar. And a lot of, especially Mr. Gopal Kumar's knowledge on this subject. There are a lot of appreciates coming. So your continuous support is required. That will inspire us to come again and again. Any comment you can direct to us. We'll try and improve our webinar or two. But also you check your mics because there are a lot of people who wanted to interact with the Gopakumar. They are unable to unmute. So probably you can check once again later in the next webinar. Check your system once again. So thank you very much, sir. Have a wonderful week and weekend and stay safe. So my dear audience, we look forward to your continuous support. We want to do much more than what we did in last 2 years. As I said, we made a record. We are one of the fastest growing engineering society. So need your support to make it as one of the largest in the world because we have over a couple of million electrical engineers in this country. As you know, India produces over 2 million engineers every year. That's what Mr. Trump also said. India produces so many engineers. So when they are looking India as a technical hub, the NFE would like to see all the electrical engineer at par with international knowledge, or probably understanding the codes and standards and international standard. We'll help you. We'll help you to get certification. So please join NFE. Thank you, sir. Have a wonderful day. Thank you. Bye-bye.
Thank you. Thank you. Bye-bye.